Afternoon, my name is Bannatyne. I'm representing VORAGO Technologies. So let me give you a bit of background about our company. We are a privately held fabless semiconductor company based out of Austin, Texas. We've actually been growing since 2004. At the end of 2015, we changed our name from Silicon Space Technologies to VORAGO Technologies. And at that time, we also became much more focused on commercializing the technology that we've been developing since 2004. Our investors asked us when we were going to start selling some parts. So in the early years, we did a lot of department defense and other agency R&D work, which gave us the ability to develop our technology, which we call HARDSIL. And HARDSIL is a way of hardening standard CMOS products by a simple modification to the processing. We have licensed our technology to a number of leading semiconductor companies who have created space products based on HARDSIL, which primarily was intended to immunize against latch-up. And we have also developed a modest portfolio of SRAMs and microcontrollers based on the ARM Cortex, based on this HARDSIL technology. So let me talk a bit about what I see as the options for CubeSats. First one is COTS. And COTS is great because you can go to DigiKey and you can get any part you like. It's state of the art, and it's cheap, and it arrives in the post tomorrow. But it's somewhat risky for a space environment. And then I see a lot of folks upscreening parts, which can get expensive. I think the last presentation was a great illustration. I've been involved in radiation testing our devices, and it's inconvenient and expensive to do that. I look at upscreening like insurance policy. You pay money to reduce risk, and the more money you're willing to spend, the more you can reduce that risk. Then at the other end of the spectrum, you've got the rad-hard parts. And typically, there's a limited pool of components in this area, and they tend to be not state-of-the-art, but they're not risky, they're expensive. And our objective with the products that we're creating is to create fully rad-hard products using a combination of the process modification with HARDSIL, and because we're using CMOS and it's a simple modification to CMOS, we can do that for less than the cost of upscreening devices. So really CubeSats are a good opportunity for a company where we can participate in opportunities where people want to selectively harden certain key components in order to reduce mission risk. So now I'm going to talk about how we do it, because there's various types of ways that radiation can affect this type of microcontroller, and different ways that we need to mitigate against that. This is a standard CMOS device. It's a complementary metal oxide semiconductor, so-called because there's an NMOS device and a PMOS device. And when you get yourself a CMOS device, you get a lot of extra features that come with it for free. And embedded on those die are millions of parasitic bipolar devices that look and act like a thyristor. Typically, if you operate the part within spec, below 125 degrees, and it's not being bombarded by high energy particles, the parasitics tend to behave themselves. But under certain conditions, for example, you get a radiation strike, it creates a wake, in its wake, a bunch of electron hole pairs. Those things can give you an unwanted charge in the area just underneath the active area where the parasitics reside. And if you forward bias those bipolars, you create a condition called latch-up. And latch-up basically is a short circuit from ADD to PSS, and you start conducting a lot of current fast. Most of the time you can get out of latch-up, get it quickly enough, you reset the device. Sometimes it destroys the device. So it's potentially a very problematic issue for CMOS devices. You see it in some other industries on account of high temperature also. So the way that we protect against latch-up is to put this implant in. There's a horizontal and vertical component that we call a guard ring. And it creates essentially a path for unwanted charge flow that is an easier path than switching on those parasitics. What it does is it reduces the arc-revel resistance, and it reduces the gain of the parasitic NPN. If the combined gain of the NPN and the PNP is less than 1, latch-up cannot be sustained. And it's proven to be a very, very effective way of immunizing against latch-up. And that's true for radiation-induced latch-up, for high-temperature latch-up, or for other types of transients that may occur on the device. So I think of it like latch-up is like a rifle shot. You can take out your part, and TID is more like slow strangulation of the device. And it's a slightly different failure mechanism. When these high energy particles are hitting the die, creating these whole electron pairs, the objective is to recombine these quickly and without switching on the parasitics. And most of the time, those electron hole pairs harmlessly recombine, and the device continues to work. Except for one area. Under bias, what tends to happen is as the radiation strikes are coming in on the device and recombining, the electrons tend to flow out of the oxide areas. And that leaves the oxide with a positive charge. But as you accumulate more radiation, you tend to get this build-up of positive charge on the oxide areas. And that, as you would imagine, attracts electrons in the P-well, so you create a path from the drain of the CMOS device there, the N plus region to then create a path, and it grows over time. And that's how you can protect TID onset as your leakage current starts to go up. The way that we spec our parts is that when we go out of our leakage current spec, which occurs about 330k rad, it becomes unusable. Essentially what happens is it brings down the threshold voltage of the device and transfers the transistor on. That's how TID gets you. There's some other radiation effects that we mitigate with a different way. So we use HARDSIL processing technology to dial in our TID performance, to immunize against latch-up. For single event upsets, we take a different approach, which is more conventional with the industry. So a single event upset on memory, we use a error detection and correction subsystem that as the CPU fetches words from the memory, inspects the word, and the way that this event works is that we can detect 2 bits and correct 1 per byte. So for every word that the CPU fetches, we can detect 8, we correct 1. If we get 2 errors, that's a problem, because that gives us a multi-bit error and it is uncorrectable. So our objective is to keep the single error down low enough to reduce the probability of getting a multi-bit error. And we do that with a scrub engine. And the scrub engine operates autonomously in the background and it sequentially steps through memory looking for bit upsets and correcting them. What that means is that words that are not accessed regularly from the CPU have something looking at them to make sure that they're not accumulating errors. Also, the way the layout is spaced out, it avoids having a single particle strike coming in and upsetting multiple bits. Part of what we did in the ion testing was, I think the worst condition that we observed was with xenon heavy ion particles at 76 degrees. We found that we could upset up to 4 physically adjacent bits, but because the logically adjacent bits are spaced out over a byte, we'd have to take out 8 before we would cause a multi-bit error in a single byte. So that's how we address the single upsets in memory. There's also logic and all the registers that need to be protected against. And the way that we address single event upsets in logic is through replacing all the latches with what's known as a dice latch or a dual interlock cell, which has 3 voting mechanisms rather than 1 per latch. And adding some other features like clock latch filters. And that means that if your clock is hit and there's a transient in the clock, it doesn't propagate through the logic. This is a microcontroller that we launched in 2015. It's based on an ARM Cortex-M0. The radiation steps at TID is 300 rad-hard. Software rate is 1 to -15 errors per bit per day. And the latch-up step is latch-up immune to 110. We did our testing at terrestrial neutron at Triumph in Vancouver, TID testing at UMass in Lowell, and heavy ion testing at Berkeley. And the procedure that we followed was very, very similar to what we explained in the previous presentation. So we've only really been focused on commercializing these products for a short amount of time. In that amount of time, we've seen quite a strong uptake in CubeSats. In the last couple of days, I've received 3 projects that have been presented that use the product that I just showed. But I see 2 typical use cases in CubeSats for this product. One is as a controller in an OPC. Now, one of the limitations of the micro is it's a Cortex-M0, runs at 50 megahertz. It's reasonably fast, but not fast enough for every OPC type of application. So I see a lot of applications that use FPGAs, and there's another use case that I often see with the micro where the micro is being used as a watchdog or safety monitor with a higher throughput processor like an FPGA. In this case, this is a Cortex-M0 FPGA, and the micro is being used to load it and monitor its heartbeat and reset it if necessary, and if it becomes reset. In fact, this is a non-rad-hard version of the Cortex-M0. The rad-hard version of the Cortex-M0 costs something like a high-end Mercedes. It's still a very expensive part for the non-rad-hard version, but you can take a lot of money out of the system by selectively hardening certain components in the circuit, like like the microcontroller, can check all other components on the board and reset them if any match up or so. Okay, the like arm, it's easy to program. It's inherently variable power with power work on reducing the power consumption. They're nice people from here in Cambridge. We have a development kit that makes it easy to develop code, and there's tons of software support for that, and that's why we chose it. We've run out of time, so thank you so much for your attention.
Thanks very much. Any questions?
I have a quick one.
Of course. As long as it's quick. I feel a bit guilty now. Anyway, do you plan to develop A2B to A converters in the future using your technology? Or just like you.
Yeah. So we're working on our next generation product right now, which is based on our Cortex-M0 floating point, and we're planning on adding more peripherals than we had on the first part. So I need to be converting the DAC between the peripherals that we're planning on adding for the next gen part. Thank you.
Any other questions? Oh, well, thank you again. Thank you.